All right, we're just going to let people wander in for another few minutes, but I've been learning about Hawking radiation from Tom, who's 6 at the back there, how you turn a black hole into a white hole. So I was just explaining to them that when I was 6, Hawking radiation hadn't been invented yet. But it's very nice to be back having another public lecture, and especially after COVID, numbers are building again, which is very good. Today we're going to be hearing from 2 of our PhD students, one of whom I think has just submitted, and Pratyasha, who's going to submit soon. So Pratyasha's come to do her PhD with Dr. Ryan Shannon and myself on pulsar timing, and Nemus has come from Bali to do her PhD here at Swinburne again. And the title of their talk is Tiny Yet Impactful Clues to Unlocking Cosmic Mysteries. So we're first of all going to hear from Pratyasha and then from Nima. So can you welcome to the stage Pratyasha? Yep.
Okay. Hello everyone, as Matthew introduced me, I'm Pratyasha, a PhD student here. And today we are giving a public lecture, me and Nemus. Before we start the lecture, I would just briefly give an acknowledgement of the country. We would like to respectfully acknowledge the traditional owners of the land on which Swinburne campuses are built on, which belongs to the Wurundjeri people of the Kulin Nation, and we also respect their elders, past, present, and emerging. Okay, without further delay, so today we are going to talk about tiny things in the universe, but they have big impact on the structure of the universe, also understanding the universe. So, first of all, let's talk about our journeys, get to know us a little bit. So, I'm a tiny person now, but believe me, I used to be even tinier. And when I spent most of my schooling and I was born and raised in this place in India called Odisha, and it gets really hot in the summers. So imagine it's a hot summer night, it's mid-July, and you don't have anything else to do. It's northern hemisphere, so mid-July. And me and my whole family, we used to just go to the rooftop of our house, and we would just lie down there for ages in the night. And we would look at the sky, and it's just full of stars. And I loved watching aeroplanes and satellites just streak across the sky, and I would love to follow them as long as I can see them. And me and my family used to play this game of how many stars can you count? And we would just lie down on the rooftop, and we would count 1, 2, 3, 4. And soon I realized that the number of stars that we can count is very less. It's around 1,000, which is very many for counting purposes. But on top of that, that's not all of the stars there are in the universe. In the universe, you have many, many more stars. Some stars you can see, some stars you can't really see with your eyes. And when I was in my undergrad, I got an opportunity to actually learn more about these stars that we can't really see. These are called neutron stars. And I loved the subject so much, I wanted to study more about these unseen stars. So I continued my research and came here in Swinburne, Australia to do my PhD. So I talked about neutron stars a little bit, but what are these neutron stars? So neutron stars are, imagine a star that is very massive, 8 to 10 times the mass of our sun. And it, at the end of its life, it runs out of fuel because it's burning so much and giving off energy. And it runs out of energy, and it goes boom in supernova. And what remains is a squished core of it that is very, very dense and very, very massive. And these are known as neutron stars. If we compare neutron stars to our sun, then imagine sun is like a gigantic elephant, and the neutron star is the size of a grape, but it has the mass of the elephant. So it's very, very tiny, but very, very dense. And the size of neutron stars is actually so small that you can fit a neutron star within the free tram zone of Melbourne CBD. So they are very, very tiny and very, very strong. So super strong. So if we compare the neutron stars again to the sun a little bit more, we kind of know now that what our sun is made up of, how it creates its energy, what is inside the core of the sun. It shines really bright, so we can see it. But neutron stars, we don't really know much about them. We know that they are made up of neutrons, but what really happens in the core of the neutron stars, we don't really know. And because it doesn't usually give up a lot of energy, or we can't really see them, it's very hard to see. But thankfully, due to this woman named Jocelyn Bell-Burnett, who actually found a type of neutron stars that emit energy in the form of radio waves. Okay, let me see how I can play this. Yes. So these are known as pulsars. These are a subset of neutron stars that each time they rotate, they emit radio waves from the magnetic field axis of the star. So imagine this as a lighthouse, and every time the pulsar is rotating, we see a pulse emission. And that you can see here on the bottom panel, a brief pulse emission every time it rotates. Because of this property, we call them as cosmic lighthouses. They are very stable in nature and they are very, very precise, and we see a pulse emission in a very timely manner. So they are always on time, and we can observe them using our radio telescopes here on Earth. So we can exploit this property using something called pulsar timing. So in this method, what we do is we have a model of when the pulse from the pulsar should arrive, and then we actually observe our pulsar, and then the difference between them is known as timing residual, and it should be very close to zero because we know so much about this pulsar and they are very precise in nature. But sometimes, due to some astrophysical sources that can cause chaos in the life of a pulsar, we see some distortions in their timing residuals, and the pulsar emission doesn't really arrive on time anymore. So one type of that source is known as gravitational waves. So gravitational waves was actually predicted to exist by Einstein here around a century ago. And he said that when very massive objects in the universe are moving around, if you imagine the universe as a giant trampoline and these massive objects just moving around, jumping around, then they are creating these ripples on the space-time, and these are known as gravitational waves. And he predicted that this could exist, and now we have actually detected them around 10 years ago, and there was also a Nobel Prize that was dedicated to the discovery of these gravitational waves. They have a very unique property. When gravitational waves are propagating, imagine the source is on the top of the screen, then the objects around it move in a very peculiar format. So the space-time is actually expanding and contracting. Because of that, the objects will move closer to each other and move apart. So if you imagine that the source of gravitational wave is kind of coming from the ceiling, then you guys would move closer to me and move apart. And in similar way, the ceilings of this room would move closer and apart because of these gravitational waves. But these gravitational waves, they are very shy in nature. They don't really like to interact with the matter strongly. But we can also explore that nature, and we can see very, very far away, and very, very far away in the time too. Like gravitational waves that have occurred, started or generated very further in time. So we can study the early phases of the universe and stuff like that using gravitational waves. Another property of gravitational waves, they are very weak. So if I can borrow my good friend Nemus over here, and imagine that we are two sources and we are just moving around, we are accelerating. In this process, we should be emitting gravitational waves. Now raise your hand if anyone felt gravitational waves traversing through their body.
Not joined.
You should get that changed. To actually experience the gravitational wave source has to be very, very massive. So if we have two black holes, very, very dense objects in the universe, of masses 10 to the power 9 times the mass of our sun, then they would perturb the space-time 1 unit per 10 to the power 15 units. So very, very tiny amount. That's why they are very hard to detect. But we have pulsars. We will use pulsars to detect these gravitational waves. Let's see how gravitational waves affect these pulsars. So basically, if we have a source of gravitational waves, then we have our pulsar, then we actually observe it with our radio telescopes. Then because of these gravitational waves, the space-time will expand and contract. So the distance between the pulsar and the observer will change. That would make the pulse emission to arrive a little bit earlier or a little bit later than what we predicted using our model. So simple, we will detect gravitational waves that way. But we have a problem. Pulsar data can be noisy because it's not that we just have a source, we have a pulsar and we have an observer. There are other things in between, such as the interstellar medium, which is the medium between different stars, and it can have lots of plasma, energetic particles, and the photons from the pulsars, it loves to interact and get disturbed by this interstellar medium. Apart from that, we also have our sun. Our Earth is going around the sun. And if you are observing a pulsar very close to the sun, then the charged particles from the sun is going to distort the arrival time of this pulse emission too. So there is a lot of signals that are coming together. So how would you distinguish between which one is coming from a gravitational waves and which one is due to other things, other noise processes? So for this purpose, we don't need to look at just one pulsar, but we need to look at many of these pulsars. And if, because of these gravitational waves, the pulsars that are like the noise sources would be unique to a single pulsar, but the gravitational wave would be common between all of the pulsars. So because all of the pulsars that we have found and now we are studying are in our galaxy, so now we have created a detector that is galactic-scale. So we didn't have to build a detector for detecting gravitational waves. We just used the natural objects around us to detect gravitational waves. So that is pretty cool. Now, how would you know that you have actually detected gravitational waves? What would be like as my colleagues like to call it, the smoking gun of detecting gravitational waves? So, as I said before, the pulsars that are close in the sky would behave in a similar way because of the gravitational waves than the pulsars that are around 90 degrees apart. So we are looking at how correlated the timing residuals are from different pulsars. And if we see a signal like this, then we know for sure that we have detected gravitational waves. So now we know what would be our detection signature. Using pulsar timing arrays, we are kind of sensitive to a very specific wavelength of gravitational waves. As I was discussing with one of the audience members before, they were asking me about which gravitational wave detectors are there. And then we have many kinds. One, we have the ground-based interferometers that detect gravitational waves. So far we have nailed that area. We have kind of detected hundreds of these gravitational wave events, which are coming from stellar mass black holes merging together. And we have also proposed space-based interferometers such as the LISA mission that hasn't come alive yet, but is proposed to be there around 2030s. But what we care about using pulsar timing arrays is this regime of wavelength, that is ear wavelength gravitational waves, and the sources of this could be supermassive black hole binaries. So how would you form supermassive black hole binaries, and what do we know about them? So on the x-axis here is the separation distance between these supermassive black holes, and a unit here is megaparsec or parsec, which is basically a distance scale that astronomers use to describe very large distances. So imagine that there is a supermassive black hole at the center of a galaxy. And then there is another galaxy that also has a supermassive black hole. Now, naturally, due to gravity, they can come together, they can merge. So if the galaxies together are coming together, then the supermassive black holes at the center of the galaxies are also coming together. And then in the end, the galaxies can merge together, and then the supermassive black holes would come very, very close to each other and form a supermassive black hole binary in that process. How do we even know that they exist? So if you remember that we had detected and taken picture of a black hole at the center of our own galaxy. So this is this picture. So we know that there is a supermassive black hole at the center of our galaxy. That means there could be supermassive black holes at the center of galaxies. We also have images from very deep observations of the sky where we see two black holes very, very close together. They're not in a binary yet, but they are very close together. So we know that that process is happening. But what happens when they come very, very close together? We don't really know. We haven't really seen yet because they become like a single blob and they are not resolvable with our current generation telescopes. So we want to understand them and we want to really see them through these gravitational waves. So these gravitational waves would impact different kind of signals in our dataset. Now imagine that you are in this room and you can't really see, but there are a lot of dinosaurs around you. And they are moving around, they are making these stomp, stomp, stomp noises. But all of them. Can everyone just stand up and make some stompy noises for me? Stomp, stomp, stomp. Yes. Okay, now you can sit down. Thank you very much. So all you can hear in that scenario is addition of lots of stomps. Okay. I saw that that was difficult, so I won't make you do it again. But that is kind of known as the stochastic gravitational wave background, where we just hear addition of signals from many different sources. Now imagine that you have the same scenario, but now there is one person, one dinosaur that is stomping really, really loud. So you can really tell it apart from all other background noises. So that is kind of continuous waves that comes from one single supermassive black hole binary that is either very close to us or very, very massive and very, very strong and loud gravitational wave signals that they are emitting. So we can really pick it apart from all of the other background noises. So that is one kind of signals that we expect. Oh, okay, this came now. Apart from that, we can also detect bursts with memory, which is that imagine if this is made out of mud plains and after you have stomped and left, it still leaves like a footprint behind of all of the signatures. So that is kind of a signal that we expect, which can come from mergers of say supermassive black holes. So now we have many big questions from this about how do the supermassive black holes form. We kind of have one idea of how they can form through these galaxy mergers, but is there another way in which they can form? How many supermassive black holes are there around us? Do these black holes eventually merge or something happens that they just stall and never merge together? And then how does having a supermassive black hole change the properties of the galaxies? And also, is there any unknown sources of these gravitational waves that we don't really have an idea about? Something new, something exciting. So there are many questions. But we now have a big task. We have our detector of the pulsar timing arrays. We know that kind of signature we expect, the signals that we expect, and now we just need to do it. Search for these gravitational waves using pulsars. So this is kind of like an international effort. Many people around the world are trying to find these supermassive black holes using this pulsar timing array. We have people in North America. We have people in China, we have people in India, and here in South Africa, we also have people in Australia that are working together towards detecting these gravitational waves. I am part of one of these collaboration groups known as the Meerkat Pulsar Timing Array, which uses the radio telescope that is based in South Africa, and it observes 83 of these pulsars very, very regularly to detect gravitational waves. Last month only we had a results release of all of our data set and our efforts on searching for gravitational waves. And we saw exactly what we were expecting. So the green curve here shows the expected correlation because of the presence of gravitational waves. And the blue curve, like the blue points, show like our data points actually. And then we found strong evidence for the presence of this gravitational wave background. So we have kind of done that part now. Good job. But now we want to understand what's there beyond the background. We kind of saw the fossils of this dinosaur. Now we want to like dust it off and find out what it actually came from. So my task here was to do another study in which I looked for a very specific type of signature that can come from this gravitational wave bursts with memory. So as I mentioned before, this can happen because of two supermassive black holes merging together, or this can happen if there is another very massive object that is coming in a flyby motion around the supermassive black hole binaries too. So these are very interesting objects and scenarios in the universe, but at the same time they are very, very rare too. So it would be amazing if we can find such a signal in our dataset. The signature that would leave behind on a pulsar would look like this. So the flat line here shows the perfect life of a pulsar, and then from this point onwards it shows what happens if a burst with memory signal is present in our dataset. It causes chaos in this perfectly balanced life of pulsars. And we want to search for this signal in all of our pulsars using our radio telescope, that is the MaidCat radio telescope. So we have now done the search, we have looked at all of our pulsars, but sadly we didn't find any significant evidence for presence of such a burst with memory signal, which is very sad. But we can do something more interesting out of that too, which is making sky maps. So sky maps basically tell you, basically divides the whole sky into a number of pixels, and across each pixel we have plotted the gravitational wave power. So imagine that the number that is plotted on the gravitational wave power on a pixel, and that basically tells that if there was a gravitational wave signal stronger than that value, we would have definitely detected it. But we didn't detect any gravitational wave burst memory. That means that the gravitational wave burst memory signal coming from that part of the sky should be less than this value that is plotted. So this basically tells us like an upper limit on the gravitational wave burst signal. So that is where kind of my current research is at. But as you saw that there is so much more to discover, we need to take a lot of data set, make our radio telescopes and everything more sensitive so we can be clear in like identifying the signatures coming from these different supermassive black hole binaries in the universe. And yeah, there is so much more to discover and unravel in the universe using pulsars. Now I would hand over to Nemus.
Thank you so much. So we already see how neutron star, pulsar, and also gravitational wave so impactful to our universe. So now I want to change to something tinier than neutron star. So what is that? But before we get off of that, so I want to know about me. So tiny mass. So my journey in astronomy began when I was 5 years old. So at that time I was living in Surabaya. So Surabaya is the second big city in Indonesia. So at that time I watched the movie called Petualangan Serena. So it means like the adventure of Serena. So at that time I saw Serena visited an observatory. So this is the observatory that Serena visited in Indonesia. This observatory called Bosca Observatory. So when I saw that, I said, oh my goodness, that's a big observatory. Yeah, I mean, this is the biggest observatory that we have in Indonesia. And then I think I should visit this observatory one day. So, and then after I finished my kinder, I moved to Bali because my family from Bali. So when silent day in Bali, we turn off all the light in one island. So you can imagine how dark in Bali when the silent day. So I can see the beautiful sky. And when I see this beautiful sky, I ask myself, how this universe work actually? Why there are a lot of stars? How the star made, by the way. So yes, that's just like inside my tiny Nimas thought at that time, because when I asked my dad, oh, I don't understand actually what is that, and then I asked my mom, I think you should go to maybe astronomy program when you go to university, something like that. So I keep it silent until I high school. So when I was high school, I'm so lucky in Indonesia, we have an astronomy competition we call Astronomy Olympiad. So I was thinking when I joined that competition, oh, I will learn about the detail of the planet and how the constellation happen, and then maybe about the astrology. That's my tiny Nimas thought. But I found a lot of physics and math at that time. As a high school Nimas at that time, oh my goodness, how I can deal with the physics and math. But lucky me, I understand physics and math because of astronomy. So yeah, lucky me, I got a medal at that competition, and that's bring me to university life. So I decided to go to university to learn more about astronomy, and I did it. So in the end of my journey in my bachelor degree, I finally have a chance to decide what the final project that I really want to do. So at that time, I wanted something that really anti-mainstream in my department. So in Indonesia, we have three big groups: solar system, stellar physics, and also cosmology and galaxy. At that time, all people more doing the stellar physics and also galaxy and solar system. But me, as an anti-mainstream person, oh, let's do a neutrino, because no one to speak about the particle at that time. And then, but I was thinking, oh, maybe I can doing the solar neutrino because I think that sounds fun, and I found this problem really cool. And then I go to my supervisor at that time, and then my former supervisor said, Nimas, actually solar neutrino already solved. I think you should go to cosmology neutrino. Oh my goodness, what is that? I have a bad mark in cosmology at that time. And then I was thinking, oh my god, it's really difficult. But this is the beginning of my journey in cosmology, and now I'm a cosmologist. Okay, that's a little bit about tiny universe. So what is the neutrino, by the way? So I know Paratyasha already asked you to stand up, but I want to ask you to stand up again. Can you stand up again, guys, please? Okay, so basically, neutrino is the tiny particle even tinier than the electron. So I want to ask you to feel neutrino for 5 seconds. How many neutrino pass on your body, across your body? Can you feel it? How many you can predict? Oh my god. A lot. How many? Can you give a guess? Let's see. Pardon?
600 million.
More? Okay, can you imagine that 600 trillions of neutrino pass our body every second? But yet, can you feel it? Okay, thank you so much, guys, for standing up for me. Okay, so although there is a 600 trillion neutrino pass across our body, but exactly we cannot see it because they are too tiny to us, because tinier than electron. But of course, we cannot feel it because I just like to feel how excited you are about the science, but I cannot feeling about the neutrino. So I said that neutrino as a ghost particle. Yes. Yeah, they are like a ghost. We cannot we hard to detect them. Although we have a detector with the size like this room, we also actually hard to detect them because neutrino is shy particle. I usually use this analogy because I always compare the neutrino with the photon one. So photon like a particle who always interact with another people. No, I mean another particle. Okay. So every time photon meet another particle, they always shaking the hand. Hi, I'm photon, I'm photon, I'm photon. But neutrino, I don't care about you. You don't need to care about me. Just give me away. That's neutrino. But although that neutrino is like a ghost and also like a shy particle, actually neutrino was an important thing to our universe. Okay, before we go into that, so in standard particle physics, neutrino has 3 flavors. Don't think about strawberry, don't think about orange, please don't think about chocolate, but this is the flavor of neutrino. So I introduce you the first flavor is the neutrino electron, the second one is neutrino muon, and the third one is neutrino tauon. So in standard physics, we have 3 flavor of neutrino. And also neutrino works with the weak force. So that means neutrino hard to interact with people, particle. So why neutrino hard to interact with the particle? Because how they interact with interaction. So that's why I said a ghost particle and also introvert particle. And also in the standard model, neutrino has no mass, but later we know that actually neutrino has a mass. I will come back with this because this is about my research project in master, and we will discuss in detail about the mass of neutrino. So where is the source of neutrino? So I will give you a little bit 3 seconds to think. What do you think the source of neutrino in our universe?
Stars.
Yes?
Big Bang.
Big Bang, good job. Another thing?
Stars.
Star, yes. Yes?
Black holes.
Oh, it could be. It could be. Yes?
Graveyards, because they're ghost particles.
Oh, interesting. Okay, so there's some source of neutrino that I learned before. So the first one is the sun or another star, actually. So this is that made me wanna learn more about neutrino. The second one is supernova. Remember the boom star that Prati said in the beginning. We will see in detail. And also in galaxy, I will tell you a little bit about that, and also in the early universe. Okay, we begin with something that are really interested in neutrino, which is a solar neutrino. I'm sorry for this thing. I know a little bit, oh my goodness, what is that, Nimas? I don't understand, but this is a reaction inside our sun. Okay, basically, inside our sun, there is a reaction we call nuclear reaction. So that's changed the proton or hydrogen to the helium. So another product other than helium is photon. So that's why you can see that the sun will be like sunshine because they produce the photon too. But another product of this reaction is neutrino. Maybe you can see like this one, the red one, the blue one, this one, the green one. This is, I think, the purple, the color, and also the yellow one. So the product of this reaction, helium, we cannot see the helium because helium still lives inside the sun. We can see the sunshine because they produce the photon, and also we can see the neutrino. Oops, we cannot see the neutrino, I'm sorry. Yeah, so if we can find the neutrino from the sun, it confirms that something happened called nuclear reaction inside our sun. And also it confirmed that our understanding about the stellar structure is right. So if you want to proof that our physics is right, find the neutrinos from the sun. But unfortunately, in the beginning of the reveal the truth, so we do the experiment called the solar neutrino experiment, and the yellow one is from the theory, but the blue one is from the experiment or from the observation to the solar neutrino. And we get something like less than our prediction. Something wrong in this. So we cannot find all the neutrino from the sun. So it means that our physics wrong or something happened. Actually, there is a solution in every problem, right? So the solution for this problem we call as neutrino oscillation. Do you remember how many flavors neutrino has? 3, yes, good. So basically, neutrino oscillation is the changing the flavor of the neutrino. So from the neutrino electron they produce inside the sun, and then move to change to neutrino muon, and then change to neutrino tawon, and so on. Okay, so basically neutrino oscillation like changing the flavor of the neutrino. So when we count all the neutrino, because before we just count neutrino electron, because based on the theory, we just like a neutrino electron that produced inside the sun. So finally, problem solved. We can find the neutrino from the sun. Yeah, but when you change the neutrino one flavor to another flavor, you need the energy. And this suggests us that neutrino should have some mass. So actually, this discovery make another problem. So do neutrino have some mass? Oopsie. We still don't know until now, still doing that. And I will tell you about what I'm doing with the neutrino mass in my project later. So from this discovery about the neutrino oscillation, these two professors, Professor Kajita and also McDougall, have got the Nobel Prize. So thanks to this professors, so we know the problem solved of the neutrino problem, solar neutrino problem. Okay, now we jump on to supernova neutrino. Okay, maybe you can have a deep breath before we jump into something new. Okay, just like to transition a little bit because sometimes tired to hear something new. Okay, so when Pratyasha said that when the neutrons start forming, there is a boom from the big star. Okay, so in the big star, inside the big star, they produce iron in the center of the star. So this iron actually made the energetic photon. So if you see something like a Y, but actually this is called gamma, this is called photon. So when this iron made the energetic photon, they turn to helium. And when this helium made the energetic gamma and turned to neutron and proton, and after that proton made the electron and become the neutron and neutrino. So that's why when Prati said that something left from the boom star will be the neutron, will be a lot of neutron particle inside the star, they also produce the neutrino. So basically, when we can observe this neutrino from the supernova, it can be a good alarm for supernova observation. What does I mean from from this? So remember that photon actually socialized particle, and neutrinos so shy. They are super shy. Okay, so when that boom happened, the supernova happened. So before that photon and neutrino come to the observer, so photon say to their friend like, hi, I want to leave you here, so I want to go to my observer and tell them, oh, there is a boom star here. Okay, and then just like shaking the hand and then ask permission, bye people. But neutrino again, I don't care about you, you don't need to care about me, I will go to my observer and tell them there is a supernova in this direction. So can you imagine what happened after that? Who will arrive first, neutrino or photon? Neutrino. So neutrino can be alarm, means that neutrino come first to observer to tell people, hi, there is a supernova happen in this direction. The later after that, some hours after that, photon just coming in, hi, supernova. So that's why if you can get this neutrino to the Earth, it can be the alarm for supernova, and the people who in charge in observe the supernova need to prepare themselves. So this is there is a thing called the supernova early system warning. Basically, they watching about the supernova neutrino and find this energetic neutrino, and can be a sign for the supernova observer in the optic wavelength to tell them, hey, prepare your telescope, we will have a supernova. This is one of the supernova detector to see the supernova neutrino. It's called Super Kamiokande in Japan. So can you see the tiny here? So this is a person. So you can imagine how big we need to build a detector of neutrino to see just like a little thing. Yes, so in astronomy, if you want to like see something very, very weak in energy, you should have an instrument that's really, really big to find it. If already bright enough, you don't need to like a big thing to observe it. But if they like a tiny and like a little energy or hard to observe, you need something big. Okay, I'm going to be quick in this because there is a lot of theory about the high energy cosmic neutrino, but one of my favorite is this. So, the one of the candidate for the high energy cosmic neutrino is from annihilation dark matter. So what does that means? So basically, dark matter with the dark matter, they just like vanish each other and make the neutrino. It will be like a high energy neutrino. So if you can get this neutrino, it confirms that, oh, dark matter, maybe there is a dark matter in our universe. Are you still believing there is a dark matter in our universe? Yes, because we are cosmologists, so, okay. Okay, so we jump to neutrino cosmology. So this neutrino make me think that I'm not enough study in my master. I should go somewhere to continue my PhD, and I end up in Swinburne because of this neutrino cosmology. Because my method that I used when I was master, same as what I did in my PhD. So I will begin my story in neutrino cosmology with the Big Bang. So when that bang happened, so it means that the time in universe started. And at that time, because of the consequence of the Big Bang, so the space of the universe from the tiny and become expanding. So in the early universe, the size of our universe very small and very hot. And it means that there is no space for neutrino to run away from another particle. So let's see, like this one, this is like a group gossiping, like actively interacting with another group, and also beside this, there's like a group who always like actively interacting with the people, but there is no space for neutrino. Just like, okay, I will interact with you, I have no option, let's interact. But because of consequence of the Big Bang, our universe expanding, the space become larger. So now neutrino has a base. So neutrino can run away from the another particle. We call this event as neutrino decoupled. And this event happened when 1 second of our universe. So imagine 1 second after the Big Bang. Our universe already created the space, created the particle, and neutrino decoupled. So this actually gives me an inspiration, and hopefully give you the inspiration that universe can do something, many things in 1 second. Hopefully as a human we can do something more to our society. Okay, that's the advice from the universe. Okay, so a little bit about observation. So when we see the sky, let's see, I want to see this direction. Actually, with my telescope, we can see like a lot of stars, a lot of galaxy. And also, if we further than that, we can find the young photon. We call it as the cosmic microwave background. This is the farthest object in the universe we can see actually in our universe. And actually, if you really want to go further than that, we also can see the young neutrino from our universe. We call it as the cosmic neutrino background. If we can see this cosmic neutrino background, actually, we can learn about the universe at the age of the 1 second, which is very young, because when we back to here, because this is the farthest object we can see in the universe, we can just see the universe in this age. But younger than that, we still cannot. So if we can observe cosmic neutrino background, we can learn something when our universe at the age 1 second, which is really, really young. And the second thing that we can learn from the cosmic neutrino background is confirm that Big Bang really happened. So if you want to confirm Big Bang really happened or not, just find the cosmic neutrino background. Okay, and then the third one is understanding about the nucleosynthesis, which is the process of forming of the element of our universe. So, by the way, unfortunately again, remember that how shy our neutrino guys? Yeah, they're so shy. And also, neutrino from the young age of universe is really, really low energy because of the expansion of the universe. So it's hard to us to detect that neutrino. For example, we have a candle here, and we compare the candle with the sun. So hard to find the candle, right? If you want to find the candle, because the low of energy. So the candle is neutrino, and the sun another energetic particle. So we are really, really hard to find this neutrino. So that's why we have a homework here. Again, I know people hate homework, but we have a homework to find the cosmic neutrino background. And if we want to have a cosmic neutrino background, we need a big detector. Remember how big detector from neutrino supernova? Yeah, even bigger than that and sensitive. Okay, so I want to talk a little bit about my project when I was doing a master's. So that's about the neutrino cosmology and the mass of neutrino. But actually why we can find the mass from the cosmology data, this is the story begin. So in our universe, we have some ingredients to make our universe work. So the first one is dark matter. The second one is matter. So a common matter like a proton, neutron, and electron. And another thing is neutrino, our favorite today, our celebrity today. So we can just make a simple analogy how to forming the structure in universe. So when I say structure, it means making the group of galaxy, and also and its friends. So we can make this analogy as make a cookie. Who make a cookie here? I know some of you a very, very in charge to make a cookie every week, so thanks for that. So we have a dark matter here. I make an analogy as a flower and also the eggs. And for the matter, I use a chocolate chip here. Who like a chocolate chip? Oh my God, I love chocolate chip. And then for neutrino, I have a butter here. So these ingredients we make to make a cookie. So if we have a lot of butter inside our dough, it's hard to make the cookie because it becomes a liquid dough. But if we have the right amount of the butter, we can make a cookie from that. So what we can learn from this? So if we have a lot mass of neutrino, it's hard to make the structure, by the way, because at that time the behavior of the neutrino destroy the formation of the structure. But if we have a less neutrino, a right amount of neutrino, finally we can make a structure. So this is a little bit about the simulation we do in astronomy. This is not my work, but one of my friend here, Dr. Stuart Lyell, doing a simulation. You can ask more about simulation to him. So this is a simulation about our universe. So basically, you can see like a filament, and also there's something clumpy here. It's a group of galaxy. So you can see if we have the less amount of neutrino, actually it's easily to make a structure. But if we have like a more mass of neutrino, hard to make the structure. Because neutrino play an important role in this making the structure. So I can extract the mass of neutrino from the data of the universe, like a cosmic microwave background, if you remember about the cosmic microwave background, and also from this large scale structure. So this is the little bit result of my master thesis. So maybe a little bit confusing you. So in the x-axis is the delta, it's the summation of the mass of the neutron or total mass of neutrino. Now in cosmology we can consider the total mass as neutrino, because actually with the cosmology data we cannot distinguish the flavor of neutrino. So how we distinguish them? We need to combine cosmology data with another data, like a solar neutrino experiment or like an atmospheric neutrino experiment. So we need like a collaborate with another thing. So this is what I get 8 years ago. So yeah, I've done my master 8 years ago already, long time ago. So I got the upper limit of the total mass of neutrino. Until now, with our model in cosmology and with our data, we can just constrain the upper limit of total mass of neutrino. Hopefully, with the new data and also many data combined together, we can get the absolute mass of neutrino. So how to read this plot, by the way? Just like a focus on the x-axis, and then see that, oh, from this data, actually CMB, this is just CMB data, I can get like 0.7 electron volt mass of neutrino. But if I combine like a more data, like a CMB large scale structure, and also supernova data, I can like have a higher constraint on that. So basically in cosmology, if we combine more data, we get something precisely. And that's a result from 8 years ago. Now in Swinburne, I'm a part of DESI. So DESI is Dark Energy Spectroscopic Instrument. So that's actually the collaboration to see the large-scale structure of our universe. So we in Swinburne is a part of DESI. So DESI team try to understand the universe with looking at a lot of galaxies. Can you imagine how many galaxies that DESI will observe? Can you have you have a guess?
Trillions.
Do you have a guess? How many?
Trillions.
Pardon?
Trillions.
Oh, that's not many much like that. So we plan like around 30 million galaxies currently. So with this many galaxies, with the first data release, we successfully constrained the total mass of neutrino down the mass neutrino come to y-axis. So when we combine the CMB data with our DESI data, it will be like a constrained tightly with this. So now we know that the total mass of neutrino cannot more than 0.1 electron volt. So we need to more data, more galaxy, and precise data to constrain this mass of neutrino. Yes, that's from cosmology side, but we still have a lot of homework. So because a lot of young generation here, maybe we can think from now how we solve this problem. So the first one, we need to find in cosmic neutrino background. Okay, so we need to think how to make a good detector and how big the detector we need to make. So the second one is determine the mass of neutrino. It can be from the cosmology, it can be from the solar physicists, or it can be from the particle physics. So we need to collaborate together to solve this problem. And the third one is, there's an extra flavor of neutrino? We still don't know. It's still a big question in particle physics now. And maybe this is a really interesting thing too. Is there another source of neutrino actually? Yes, we have a lot of homework, by the way, if we place it. Okay, that's all my talk. So if you have any question, please give to us and we can discuss. Okay, thank you so much.
Yeah, thanks very much for those wonderful talks. I was very proud to be a Swinburne staff member and have such bright students. So let's give them another applause. But there is an additional test. Can they answer questions? So we open it up to the floor. Yes.
I think the first lecture I ever came to was when, with my son, was we just discovered the gravitational waves with our planetary-based interferometer. Is that correct?
Yeah.
Yep.
So, and then you're saying that with pulsars we can detect them. Has that been since then? Because I thought that the planetary-based one was the first evidence of it, but maybe I was wrong.
Maybe you want them to the microphone.
Yes. Yeah, you are right. The first ever detection was through the ground-based interferometers on Earth, and we detected gravitational waves from black holes that are as massive as 30 times the mass of our Sun. But the one that I was talking about using pulsars, we can detect gravitational waves 10 to the power 9 times the mass of our Sun, that massive black hole.
Right.
So it is gravitational waves, but from a different type of source. They do.
Further away, therefore.
They are very, very far away.
Yeah.
Yes. And they are like at the center of these galaxies, and we don't know much about them. So that is more interesting because now we have found like hundreds of these gravitational wave events from stellar mass black holes using the ground-based telescopes. So we want to detect something more exciting and something that we don't know much about. Yeah.
Right, thank you.
I just wanted to ask you, what's the most recently discovered thing in the universe that has been discovered yet?
Do you want to repeat the question?
I think the question is, what is the most recently discovered thing in the universe that hasn't been discovered yet?
Yeah, that has been discovered.
So the last
already.
thing that was discovered.
The last big thing.
Oh,
Maybe you can answer.
I can think of something not related to my work, but something that JWST, that is like infrared telescope in the space, discovered, which is called these binary planets, which I thought was very interesting, and we didn't really know that they exist because we always know that there is a sun and we have planets that go around the sun. But JWST actually found planets that go around each other, and there is no really clear sun around it. So that is very weird. We didn't know we would see something like that, but we saw something like that. So now there is so much more work that is going on in understanding how these binary planets form. Why are they going around each other? So that is something interesting. Recently that has been discovered that wasn't discovered already.
Yes.
Sorry, just on neutrinos, I just saw recently somewhere in the news that a very high energy neutrino was just found, or it was discovered or sensed only a couple of days ago at the bottom of the Mediterranean. It was a lot higher energy than they've ever measured. Any idea of what the source would be?
So so the question is recently there is a news about the discovery the high energy neutrino, and the question is what the potential source of this high energy neutrino. So I saw that video actually a few days ago about that. So when I watch it, that's not clear what the source of is produced the high energy neutrino, but my thing at that time, or maybe from the AGN. So AGN is active galaxy nucleus. So the galaxy who has a very active center, so it can make the neutrino and high energy neutrino. So it may be of that, or maybe the annihilation of the dark matter too. So we still need to make the like a model to understand what can produce that high energy neutrino. Yeah, that I just like saw some news like from the website a few days ago, and very interesting for the future of the neutrino discovery. Thank you so much.
All right, this gentleman over here, and then we'll go at the back, and then we'll come back to Tom's mate.
Hi, thanks for the lecture. I'm just interested to know if you think we will ever see beyond that 380,000 year limitation. Is it a technology limitation, or is it more to do just with physics and the expansion of the speed of expansion of the universe?
Okay, so the question is why we can just like see and just in the age of the universe 380,000 years old. That's about the limitation of our instrument or something else. Is that true?
Yeah.
Yeah. So let me think a little bit. Okay, so because we have a expanding of universe, so every time come from the past have a low energy come to us because universe expanding, and when they arrive to us already like a low energy. So we need to be deal on that. So when as I said before, if you wanna see something with the low energy, you need something big to detect them. So I could say that for this, why we can just like see after that. Actually, in the history of the universe, something happened before that 880,000 years is actually universe just like do nothing, by the way. But before that, before doing nothing, actually they form the element, and before that is neutrino decoupling. So that's a limitation of our instrument now. So if you want to go further than this object we call CMB, we should have a powerful instrument. So that's why I said we need to make the big detector to find the cosmic neutrino background. Because if we can see this cosmic neutrino background, we can just reveal the process of the formation of the element and also another story of our universe. But basically, in our theory now, between the cosmic neutrino background and this cosmic microwave background, our universe almost like a peaceful universe.
So it's a technological limitation or a physical barrier because of the speed of expansion of the universe?
Yeah, in my opinion, that's about because of the limitation of the instrument we have.
The light didn't used to go in straight lines until the universe was 380,000 years old. So you're looking at light that's come from random directions, and then it can go in straight lines. But prior to that, you can't observe anything with light earlier than that because of the scattering. But if you could observe gravitational waves or something, or like neutrinos, you might be able to go further back. And so the polarization of the cosmic microwave background is one way to explore how the universe looked when it was very young, and quite controversial. Go to the back.
Just on the flavour of the neutrinos, do we know why they oscillate? And do we also know if the cosmic neutrinos also oscillate like the solar ones?
Okay, so basically when neutrino come from somewhere else to us, actually they should be oscillation, by the way. So because of the nature of neutrino, I could say, so what until now from the particle physics people, so suggest that happen because neutrino have an energy, and that's the natural behavior of neutrino. So that's why they do an oscillation. They should be do oscillation because that's the natural of neutrino behavior.
Okay, we've got Tom's friend.
Would it be possible that neutron stars would also produce neutrinos? Because also, as a neutron star is formed, well, the neutrons are formed, and the formation of neutrinos seems to be related to the formation of neutrons, as well as pulsars emitting radio waves, which is also emitting things which has slight similarities to the sun as well, which would also...
So I think the question is, when you form a neutron star, will you get a lot of neutrinos?
Yes. Yeah, so maybe I can back to here. So when we're creating the neutron star, basically this history of the, oh my goodness. Okay, this one. So this is the beginning of the neutron star, by the way. So neutron star come from the big star, and then they boom, become a supernova, and left the neutron star. That's the quick history of the neutron star. In the process, they produce the neutrino too here. Yeah. So basically, when neutron star, and if you see the pulsar somewhere, it should be before producing the neutrino. So always producing the neutrino with this scale.
Okay. And do neutron stars or pulsars produce neutrinos and in a process which then makes them then emit the radiation? Like, would that be possible?
So that means that after they produce the boom and then become the neutron star, will they produce another neutron, you mean? Neutrino?
Will they, yeah, so will they keep producing neutrinos maybe in the same reaction that produces the radio wave?
Okay, that's an interesting question, but currently I cannot answer that because there is no evidence that neutrino will produce in the process after that. I will keep learning, you keep learning, and we can discuss later. Sounds good, right?
Okay.
I will just add that yes, neutrinos are produced when the neutron stars are being formed, but the process of emitting the radio waves that comes from energetic particles like electrons and may not necessarily be neutrinos, I think.
Okay. All right, let's thank our speakers again. And I want to thank all of you for supporting the public lecture series, and I think I might be giving the next one. I'm not sure. But it'll be in April sometime, so thanks very much. And I promised to young boys up there I'd show them the solar system in my 3D theatre, but any other kids that want to tag along, hang around with me and we'll go up in about 5 minutes. Thanks very much.
Thank you.